Hi, everybody. So if you didn't do or watch the video where I did the simulation first, watch that one first. All right. This should be the second video you watch here in week 6. I'm going to show you how to solve a problem using Snell's law and on total internal reflection. But I want you to see what it looks like from that simulation video first. So if you didn't watch that one first, pause this one, come back to it, go to the other one where you can actually see what it looks like when total internal reflection happens. All right, here we go. I figured this would waste a little time, but I figured you wouldn't mind. Okay, now on the simulation, what I wasn't able to do because of the way the simulation worked was kind of flip it around. Here I'm going to flip it around so it makes sense, right? Here is my surface. Okay, the solid line is always the surface, and the dashed line is always the normal. So up here I'm going to have air, and air has an N of 1.00. The index of refraction of air is 1.00. Down here I have water, because it makes sense to have water below air, right? Air would be over water. And water has an N of 1.33. Now what's going to happen in this particular simulation, or this particular example, is that light is going to come out of the water at a particular angle. And since light is coming from the water to the air, right? That's what makes this work. In order to get total internal reflection, light has to speed up. I'll say that again. In order to get total internal reflection, light has to speed up because it has to bend away from the normal. You only get total internal reflection when that light bends away from the normal so much that it's going 90 degrees, okay? So we have to go from the water to the air because you have to go from a higher end to a lower end to get light to speed up. That's how the speed of light with the index of refraction works. When you go from a higher to a lower end, light speeds up. If light speeds up, it bends away from the normal. So we want this angle to be large enough so that when the light is trying to come out of here, it's not, right? Or essentially, the angle of refraction, theta 2, is 90 degrees. That's that critical point. This angle, when this angle is big enough so that theta 2 is 90 degrees, we call that the critical angle. Okay? And our job is going to be to solve for the critical angle. In this particular case, the critical angle for light going from water to air. But, and you're going to do a couple more examples before the quiz on Friday, you need to know that depending on what these two substances are, the critical angle can be different things. If this is water, like we're going to do now, the critical angle is one number. And you kind of saw what that number is about in that simulation. But if this is glass to air, it's an entirely different number. If it's from glass to water, light is still going to speed up, but the critical angle is going to be an entirely different number. But this is how we solve for that number, no matter what these two things are. We're going to use water and air, but you can use whatever two things your problem says to use if you follow this process. So let me show you how we're going to use Snell's law to solve for theta 1, the critical angle, that makes this angle, theta 2, be 90 degrees. Okay? So Snell's law, we know is this. N1 sine theta 1 equals N2 sine theta 2. And since we're going from the water to the air, water is going to be N1, air is going to be N2. So N1 sine theta 1 equals N2 sine theta 2. So let's plug in what we know. N1 is 1.33. Theta 1 is that unknown critical angle. We don't know what it is. We're trying to find what that critical angle is. All right. N2 is air, 1. And theta 2 is 90 degrees because that's when total internal reflection starts. When this angle is large enough that the light doesn't get out anymore. All right, because remember, it's big, it's bigger, it's bigger, and then all of a sudden, boom, it disappeared. Well, that happens when the angle essentially is 90 degrees. So theta 2 is 90 degrees. Now you can go ahead and get out your calculator if you want to and type in sine of 90 degrees equals, but if you're pretty good at your trigonometry, or as you get good at it, doing more of these problems, you'll recognize that the sine of 90 degrees is 1. All right, so I'm going to simplify up here. 1.33 times the sine of theta 1 equals 1, because n2 is 1, times 1, because the sine of 90 degrees is 1. All right? So both of these things on this side, for this problem, not for every problem, it all depends on what the n is, but the sine of 90 degrees is 1. So that's 1 here. So then I'm going to do some algebra. I'm going to divide both sides by 1.33, right? Because I want to find theta 1, so I've got to get it alone. All right, so now this cancels, and what I have is sine of theta 1 equals 1 times 1, 1, divided by 1.33. Now, remember, this is where you definitely need to get out your calculator. And you're going to use that inverse sine button. On this calculator, it's second sine. It might be different on your calculator. But I want to find out what angle has a sine that's equal to this. So the first thing I do is I figure out what this is. So I'm going to go there. 1 divided by 1.33. And that number is 0.75. So the sine theta 1 equals 0.75. All right? 0.751873, blah, 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 blah. But 0.75, that's fine. 2 sig digs is fine. Now, what I need to know is the inverse sine. I need to know the angle whose sine is that. So I go second sine of my answer. I'm going to close my parentheses. And I get 48.8 degrees. Or 49 degrees if you round off to 2 significant digits. Now, that shouldn't be surprising. If you watched the other video, the one with the simulator, where I was moving the light beam around and you could see that there isn't, it comes out, it comes out, it comes out, oh, doesn't come out anymore, you would have guessed that this answer should be around 49 degrees. Again, if you didn't watch that first, go back and watch that first, then come back and do this, all right? But that's how you calculate what that critical angle is. And that's what this is called. This is the critical angle for light leaving water into air. At 49 degrees, light no longer gets out. Less than 49 degrees, it gets out. At 49 degrees or larger, it does not get out. And what we have is total internal reflection. All right, go ahead, watch this video a couple more times, see how I talk about it, see how I set it up. I'm going to give you a couple of practice problems to work on tomorrow and Thursday, and I'll put the answers up on Thursday so you can see if you're doing them right. All right, good job, everybody. Thank you.